In this video, we are going to discuss genetic algorithms as parallel search. I have mentioned this before several times that there are many areas in AI that are of interest, were of interest, and still will remain in the context of AI very, very focused, and people will find a lot of interest in that. And one of which is called genetic algorithms as parallel search. Before I come to that, let's just review. So far, what we've studied are problem-solving methods in general and elaborated on various search strategies that help us solve problems through search in problem trees. Problems are represented in the form of trees, and then we travel downwards in the tree to find out the solution or solutions. Information about the tree traversal, going through the steps, was stored in memory. Typically, it is stored in memory. Therefore, we know the links that can lead to the goal or goals if there are more than one. However, sometimes we don't really need to remember where we came from, what steps we took, the links that were followed. Let's say in large problem spaces, we often use techniques in which we don't need to keep track of all the history in the memory, right? The problem space is too large anyways. So while you're searching and you're also maintaining, that would become more or less overwhelming. Likewise, in ill-structured problems where the requirements are not clearly defined, right? We don't exactly know the initial state, the goal state, and then the operators. A typical example I mentioned was that of someone trying to, let's say, design a house, an architect. He doesn't know where to start from. He doesn't know where to end. Okay. I might like one design, my family likes another, your friend likes something else. And so this problem, if we were to do that, computationally, almost impossible to actually represent and then follow the steps. A typical example of ill-structured problems. In certain other problems, we might employ techniques where the only objective is to find the solution, not how we got there. A typical one I always quote is theorem proving in mathematics, or finding if life exists on Mars, discovering a new compound for chemicals and chemical analysis. If you remember, we've only performed what we call as a sequential search, going through one step, the other step following sequentially, and one person doing that. Or in adversarial search, of course, two people, but sequentially going through. Interestingly, we can follow a parallel search approach as well in order to speed up our search process. Okay. Now, starting from how do we do this? What we do is we start from multiple locations or states, initial states, right? Multiple ones in the solution space, and try out the search in parallel. You approach it problem from one direction as well and the other, and try to do things apparently in the form of parallel approach. Although this is literal sense not parallel, in the sense that you've compute this thing in parallel with this. No, it's not that. Let's take an example. Suppose we are trying to climb a hill. Our goal is to reach the top of the hill. How do we get there? We apply different operators, meaning steps go right, left, forwards, backwards, and so forth. So we will use different operators at a given position and then move in the direction that gives us improvement, meaning more height, because you're trying to climb a hill. What if instead of starting from one position, one initial state only, we start the climb from different directions, different positions, as we see in the diagram. Now, in that situation, it's a very rough description, and you can see, we are approaching the hill from to independent directions. So in other words, we start with different independent search instances, so to speak, copies of search that start from the different locations and then move up the hill. Furthermore, also think that we can improve upon this approach, individualistic approach, using a collaborative approach. Collaborating means you talk to each other, you help each other out, and tell them this is what I found, and the other one tells you I've found this one, so you compare your notes, and that's what collaboration means. So these instances interact and evolve by sharing information between themselves. And we'll find out what we mean by interact and evolve. So in other words, what I said before was we can implement parallelism in the sense that the instances can interact and evolve to solve the solution. Okay. So you're approaching problem from various perspectives. Such implementations, by the way, and that's where the topic actually comes from, such implementations are motivated from the biological concept of evolution of human genes. Evolution of human genes. How human beings, they move from one, let's say, generation to the next, and then certain other characteristics that will come across. So hence the name genetic algorithms, okay, coming from the concept of human genes. So as I said, the idea is to actually somehow use the concept of genetic algorithms as a parallel search in certain problems and reduce our time and get a faster result. So let's go, before we do that, let's go through some simple concepts. As I said, it comes from basic human genetics, concepts. Multiple search paths in parallel. Each step, as I said before, current states, okay, where each of your search person or problem is situated. At each state, the current states of different pairs of these paths are combined to form new paths. Okay, not just moving from one to the next one, but this one here, one state, this one here, another state, they combine, exchange notes, views, and then move jointly together in that sense. Okay. So rather than remaining independent, they instead they share information with each other, and thus try to improve the overall performance. So let's look at a very basic genetic algorithm. Let's start with the general population. Let's take an example. Start with a population of randomly generated solutions to a problem. You have generated random starting positions, and repeatedly what you do, number 3, let's call it, evaluate each of the solutions. So you randomly select some solutions and evaluate each one of them using the tester. Remember, I've said this before. The tester is a function, something that tells you that this, in the case of chess, for instance, that board position, whether it's a goal or not. And if it's not a goal, in genetic algorithms, you keep the best of those solutions, best meaning closer to your end, closer to your need. You keep the top 10, let's say, out of them and discard the rest. That's by collaboration, finding out the best amongst them. Then you produce the next generation of solutions from these that you have shortlisted now, and using what we call as inheritance and mutation. And then quit when you have found a satisfactory solution or you have run out of time. Suppose we are given a number of computer words represented in 32-bit format. Okay, a number of 32-bit computer words represented in 32-bit form. Remember, the basic storage unit, representation unit inside a computer in a binary system are single bits. They can either be 0 or 1. So each word that we talk about could be represented in the form of 32 bits long, okay, 0, 1, 0, 1, 1, 1, whatever that is, okay. So you are given a number of 32-bit words, computer words, and let's call them computer words rather than saying that, let's call them individuals because we're talking about genetics. So let's call them individuals, okay? Those 32-bit words. Now what you want to do is, from those individual words, you want to find out all those words, the words that have all 32 bits as one. So there'll be one of them. There'll be only one word in 32 bits for which all of the bits, the 32 bits, are ones. There are no zeros in those 32 bits. That's what you're looking for. Let's see how we do it. Okay. As I said initially, you start with random starting points, initial state. So let's create 100 randomly generated 32-bit words. Okay. These words can be, for example, the word tour, T-O-U-R, okay, or the word for, F-O-U-R. They can be represented in 32-bit format in ones and zeros, totaling a number of 32. Now, so once you've selected 100 sample words, and we don't know whether the word tour or for that I just mentioned, if I were to represent them in ones and zeros, would one of them have all ones in it? I can't say that. You can try it out. We'll look it up as we go along. All right, so what do we need to do with those 100 randomly generated 32-bit words? For each word, count the number of bits in there. Simple as that. Just pick up the 100 words, start looking from 1 to 99, 1 to 100. Look at the binary representation, count the number of ones in each of them. Exit, close your search if any of these 100 words have all 32 bits set to 1. As I said, there'd be only one word. Multiple words would mean the same thing if they have all ones, or all zeros for that. Okay, so if you don't find any such word, then what do? You pick up the top 10 words out of them. And what are those top 10 words? Which have the maximum number of ones in them. Maximum number of ones. 32 bits. Some are zeros, some are one. Count the number of ones and keep the top 10 separate. So let's say you could have a word which has 19 ones. Another word has got 20, could be 28, 17, 15. So pick up 15 number of ones in that word. Pick up the top 10. Keep them separate. And discard the other 90. Okay? So you have actually randomly selected 100, but chosen the best out of them so far. Now, from each of these 10 words that you have kind of shortlisted, we generate 9 new words from each of those 10. We generate 9 new words. How do we choose them? We pick up one word, okay, and flip one of the bits from the 32 bits. Okay, flip, meaning if any of the bits is 0, make it 1, or if you want, you can switch 1 to a 0. But in this case, you will want to switch from 0 to 1 because you're looking for a word that has all ones in it. Okay. So pick up one of the top 10s, look at the bit pattern, randomly select only one, okay, of the bits and make it a 1. Make that 0 into 1. This is what we mean by small little change. Okay, so this is what I refer to as mutation. This is mutation, small random change, as opposed to, okay, to generate new words. We'll talk about inheritance maybe later. Now, notice the mutation, as I said, can be as simple as just changing one bit of the 32. We could make it 2, we could make it 3, and so forth. But we're trying to illustrate the concept. We just take one bit and flip it. Now, repeat this algorithms until we either get our required 32-bit word from the ones that we've now created, or we run out of time. Well, if we found the results, that's it. If we don't, we run out of time, we can say, all right, we couldn't find what we were looking for. Understand? So this is looking for a word that has all ones in it using random mutation or just mutation. Now let's do the same thing, but use another technique, all right, which is called crossover. What do we mean by crossover? Same thing. Start with the 100-bit words, 100 words randomly selected, and count the number of ones as we did before. From all those hundreds, count the number of bits 1, which are, if you find a 32-bit, all one set to 1, you say you found a solution. If not, keep the top 10 words, as I said. So far it's the same as before. Okay, discard the rest. Select the top 10. Now, from the rest of the 9, okay, you take 2 words each, okay, and then combine your word A and you've got a word B from those 10. And from each of these, what you do is you divide the word you have into 2 parts, okay, divided by half. So you have a head and a tail of that word, meaning 16 bits on one side, the other 16 bits on the other side. Let's just cut them, okay. So simple as that. What we do is we perform crossover in the sense that we take the head, the left side, the first part of one word, and mix it, join it with the tail of the other. Okay, the first 16 bits of word A combined with the second 16 bits of word B. Likewise, the other word will be the first 16 bits of word B to the second 16 bits of word A. And this is how you will actually create new words. This is actually shown in the diagram as well. If you look at the words, half from one, half from the other. So A is all these bits, as you can see, and B is given down there. You combine, you create a new word called C, where the first 16 bits are taken from the first half, which is the head of A combined with the tail of B. Okay, so here's that cut I mentioned, dividing that into 2 parts. Right. So now, if you compare the 2 approaches, the mutation, random change of 1 bit, as opposed to this one where we're changing the head and tail together, okay, crossover. Now, if there's a likelihood that this crossover might succeed faster as compared to the 1 bits. However, if when we change these heads and tails, there's a likelihood also that you might miss the solution altogether. A pure bad luck, let's say, maybe none of the first randomly generated words have, let's say, bit number 17 set to 1. Okay. And as you go along, this 1 will never become, this 0 will never become 1. Okay. So yes, it is likely to succeed because it's changing bigger number of bits. But if by bad luck, if you miss out one of them, that could be crucial, then you won't find a solution at all. However, in the first case where you were changing 1 bit at a time, this is a slow change. This is a slow change, right? It might happen. Of course, it is likelihood that it may not succeed as well, but it's more likely to succeed because you're only changing 1 bit at a time, 1 random bit, right? And over a period of time, you might still reach your goal. So in general, and this is where I like to close this topic, the best technique in general is a combination of both crossover, head and tail being switched, as well as mutation, which is changing random bits. So if you use a combo approach, it has been observed that this does perform better than these 2 individual ones. I hope this has been useful. We will discuss further things in the next video. Thank you very much.